Hey folks, in this video we're going to be looking at my friend Q equals m times c times delta t. Q equals m cat, as I will say. So we got a few objectives here. I want you, dear viewer, to be able to define heat capacity. Do you have the capacity for that? I'm sure you do. I would like you to be able to use the equation Q equals m cat. This is a delta, but I'm calling it an A because it's fun to say I'm cat. Great, that's not a ton. Let's get going. Heat capacity, what is it? Well, I want you to remember one thing for starters. The temperature is a measure of the average kinetic energy inside a sample. So how fast those particles are moving. It's at least corresponds to that. So Q, my friend, heat, is a transfer of energy between two substances. Cool, we good on that? All right, so let me ask you a question. Let me ask you a question right here. If you got 10 grams of water and 10 grams of iron, and they're both at 25 degrees Celsius, and they both receive 10 joules of thermal energy from their surrounding, they should get hotter if they're receiving energy. What's going to happen? Which substance is going to have the higher temperature after receiving that energy? Do you think it's going to be the water? Do you think it's going to be that iron? Or do you think they're going to have the exact same temperature? Pause the video, think about that noise. All right, well, you done pause the video and thought about it? Ha! If you said anything but, well, actually, which is going to have the higher temperature? It's actually going to be iron. I didn't answer the question here, but they're not going to have the same temperature, and that's because they have different heat capacities. What is heat capacity? Well, heat capacity is the amount of energy that's required to raise the temperature of a substance by 1 degree Celsius. And I should specify that that's for a specific amount, to raise 1 gram by 1 degree Celsius. We'll see that more later. So something with a high heat capacity is a substance that requires a lot of energy to raise the temperature 1 degree Celsius. Water has a pretty high heat capacity. It takes a lot of energy to raise water's temperature by 1 degree Celsius, especially compared to that iron. Iron has, on the other hand, a low heat capacity. This substance requires very little energy in order to change the temperature. You don't need a lot of thermal energy to raise the temperature by 1 degree Celsius. So that 10 joules of thermal energy that we looked at up here, this is going to raise the temperature of water a little bit and raise the temperature of iron a lot, because iron has a small heat capacity. Let's look at that and how we're going to do some calculations. So the heat capacity is used to determine how the heat flow, how much of a substance is present, or also temperature changes. We're going to look at all these different things in our calculations. But just so you know, heat capacity we're going to represent with a big old C. And these are the things we're going to be interested in. C, my friend Q, or heat flow, and also delta T, the change. Remember, delta, that triangle means change. Change in capital T temperature. So we're going to be using this fun equation, the Q equals mc delta T, or Q equals mk. And in this, as set up here, Q is equal to the heat flow. We're typically going to measure this in joules or other units of energy. M is going to be the mass of our substance, typically measured in grams. C is our heat capacity, which is usually measured in grams divided by joules degrees Celsius. But you might see that other ways. And delta T is our change in temperature, which is equal to the final temperature minus the initial temperature. Anytime we have a delta or change, we look at final minus initial. So delta T means final temperature minus initial temperature. And we're typically going to measure this in Celsius, or sometimes a cool unit called Kelvin, which I haven't really mentioned in any of my videos. So as long as we know 3 of these things, 1, 2, 3, we can find the 4th. And that's cool. That's how most of our mathy problems are going to go down. And one thing we have to know is that every substance is going to have a different heat capacity. Even water, if you have water as ice, or water as a liquid, or water as steam, those all have different heat capacities. And so heat capacity can be measured actually in different ways with different units. I set up here, typically it's going to be this way. I'm going to always present it in this way. Usually presented in that way, but we could talk about our specific heat capacity. This measures joules required to raise 1 gram 1 degree Celsius. This would be our specific heat right here. We could also have our molar heat capacity, and that measures how many joules are required to raise 1 mole by 1 degree Celsius. And note that that is not going to be the same thing at all. Typically a mole is going to be more than 1 gram, unless we're talking about hydrogen. All right, so sweet stuff. Let's look at how we're actually going to do some of these calculations. When we're solving a basic heat capacity problem, I typically determine which of the variables are known and unknown. I determine whether Q is going to be negative or positive based on the phrasing of the question, because that's important. And for basic problems, there's typically going to just be 1 unknown. So I'll figure out what I know. I'll plug all the Johns into my equation. I'll isolate the unknown variable. And yeah, that'll do it. So let's try this problem right here. We'll do this one together. 55-gram sample of water receives that many. Yeah, you can read this question. So I'm going to read it as well, and I'm going to pick out, see which of these are known and unknown. Well, I've got 55 grams. That's something I'm told. That should be mass. That's a mass thing. I got 400 joules. Joules is related to Q. That's my heat flow, my energy flow. I'm asked what is the temperature change, so I don't know this. And I've got the heat capacity there. All right, so I'll record all the things that I know. And I'm told that it specifically receives, this water sample receives that thermal energy. So Q should be positive, I believe, in this example. We should be getting thermal energy. All right, so here's my equation. I'll plug in what I already know. Let's see, I can condense these goobers here together. And if I want to isolate this dude, I should divide both sides by 238 joule per degree Celsius. These joules are going to cancel out with those joules. This Celsius is going to flip to the top when I divide. And sweet, that gives me my delta T. Real easy, pretty easy. I just got to read the question and make sure that I am queuing into what I know and making sure I plug things into the equation correctly. And here it's important to note that we receive that energy so that we make sure that we have a positive change in temperature and not a negative change in temperature. So let's try some more practice. Here we got a question. 856 grams of iron is cooled from 96 to negative 100. Wow, why? What is the heat flow experienced by this iron? Yeah, why is it getting so cold? Whatever. See if you could try this problem. What is our heat flow in this one? Pause the video and give it a shot. All right, sick, you done did that. Let's talk about it together. So I'm going to say, all right, here are the things that I'm told. I know I got a mass here. I got a temperature, initial and final here. They're asking me, what is heat flow? I got C, and they tell me that it's cooled. All right, that's important. I could see that it's cooled here. That's pretty obvious. But let's see what do we know. We don't know Q. We asked what is the heat flow. We do know M, it's 856 grams. We know C, it's given to us nice and pretty over here. And we know the temperature change. We know it ends, the final temperature is negative 100, and the initial temperature is 96. It's from that to this. So this is final and this is initial. So we'll do final minus initial. Our temperature change is negative 196. All right, cool. Well, we can start plugging this Johns into our equation, but we should know that Q should be a negative number, and it definitely will come out that way. If we plug everything in, so we don't know Q, but we do know all these other pups, well, it's as simple as just plugging that into our old calculator and getting this fancy number. Cool, and we could express it that way, or we could express it in kilojoules. We could do regular notation, scientific notation. We could change the units if we wanted to. Get fancy on that fool. Let's try this next problem. Pause the video, give it a shoot. All right, sick. You done gave a shoot to this. Let's talk about it together. We got some air, and it's heated from 0 degrees Celsius to 70 degrees Celsius when it absorbs 800 joules of energy. What is the mass of this sample? Okay, so we have a initial and final temperature. We have a energy. We're asked what is the mass, so we're going to be solving for M. And we have C. So let's just write that down again. It absorbed 800 joules, so we know that this should be a positive number. We'll get that positive in there in a second. We don't know mass. We have C, and we have our change in temperature. It ended at 17. It started at 0, so final minus initial. Final minus initial. Final minus initial gives us 17 degrees Celsius. All right, so let's see what we got for the old plug-in Aruski. And let's move my face. Why'd you go over there? So what do we know in Q equals MC delta T? Well, we've got our 800 joules. We can plug that in. We can plug this guy in. Oh, and when we do 1 times 17, that's just 17. All right, so we'll divide each side by 17, and we get our mass is 47 grams. Cool beans. Well, that's the end of this video. I hope you feel cool about how to calculate the amount of heat transfer or variables, other variables, mass. We could also determine specific heat. We could figure out change in temperature. Lots of fun stuff we could do. Anyway, that's the end of this video. Sorry. Ta-ta. Have a great rest of your life.